So let's look at sampling. So we're converting from a continuous time signal into a discrete time signal, which can be stored on a computer and processed digitally. So one very fundamental question is, when can you sample a continuous time signal and then exactly reconstruct it from the samples? And really the question we're asking is here, how fast do you need to sample? That's another way of asking that same question. And one way to approach sampling is to think of multiplying the continuous time waveform by an impulse train. So this is this function pt, which is the summation of delta functions, where each delta function in that summation is offset by an integer multiple of capital T, which is the sampling period. Okay, so that is shown as the blue arrows in the picture above. And if you take your function and multiply by that sequence of delta functions, which in pt they all have the same height, but when you multiply them by your function xt, then they will all have different heights as shown in that picture. And as the picture shows, the smooth blue continuous time waveform matches with all of those samples, but also the green waveform also goes through all those sample points. And you could think of all sorts of other waveforms that also go through all of those same sample points. So that question above is a very important question. How fast do you need to sample so that you can actually reconstruct the original signal and go backwards? So if you'd sampled the green signal and then reconstructed, you probably would have got the smoothed out blue signal as a reconstruction. So in this case, for the green signal, if you sampled at the rate that's shown there with the delta functions, you would not have sampled fast enough. That's what we're going to be finding out. The quicker, the more variations that happen in the signal that you're sampling, the faster it changes with time, the faster you need to sample. Okay, so you can work through the maths. It's important to be able to do that, to understand that what's going on. And an important thing here is the fact that in the frequency domain, when you multiply things in the time domain, in the frequency domain, you're getting a convolution, and that's shown in the first line there in black. Okay, so when you multiply your signal xt by the sampling impulse train pt, as shown in blue, in the frequency domain, you're going to be convolving the Fourier transform of your signal with the Fourier transform of the impulse train. So we need to look at what that Fourier transform is. So this shows what is happening in picture form, as well as showing the mathematics. So the first picture, and it's very important to understand it in both the mathematics as well as in the pictures. So here, the first picture is the Fourier transform of the signal that you are sampling. And it's a low-pass signal. It only exists between values of frequency of minus omega n and omega n. Okay, so in the frequency domain, it's what we call low pass. It does not have any high frequency components. And the maximum frequency, the highest frequency component that it has, is omega n. And this might be like my voice speaking. I can't make sounds that are much higher than about 3 kilohertz. And I can make some low frequency sounds, but I can't make them above about 3 kilohertz. Just through the shape of my voice box and my vocal cords. Okay, so that's a typical low-pass signal. And then below it is the Fourier transform of the impulse train in the time domain. It turns out that is also an impulse train in the frequency domain. And so convolving those two gives you the black picture below. And you'll recall that when you convolve a function with a delta function, it puts that function centered at the location of the delta function. So in this case, when you're convolving the signal at the top with a whole series of delta functions, then your signal is going to appear at the location of each one of those delta functions. And so that's what happens here. And just remind yourself, why are we convolving? We're convolving in the frequency domain because in the time domain, we multiplied the signal by the sampling delta train of sampling signals. So the multiplication in the time domain was convolution in the frequency domain. That's why we're showing the convolution here in the frequency domain. And you convolve your signal with the deltas, puts your signal located where those deltas are. And that gives you the black picture there. And importantly, you can see if your sampling rate is slow, for example, if omega s was smaller, then you would have the picture at the bottom. So the copies of each of the signals Fourier transform, which are appearing above omega s, they would be closer together if omega s was smaller. And then when you're adding them together, because they are all added, because it's the addition of each of these individual copies, you will then get the blue signal at the bottom, the blue waveform. And in the frequency domain, if they're overlapping like this, then it means it's not possible to recover the original signal. And so that would be an indication that you have sampled too slow, because your omega s was too small. So your sampling rate was too slow. And this is going to be an important criteria. And you can see there, I think you can see pictorially, you could see that if omega s was smaller than twice omega m, then they're going to overlap. And so that actually gives us a very important criteria. And so here we have the sampling theorem. And I've drawn 3 balloons there because it's a very important theorem. I want to highlight that, its importance to you for the whole of signals and systems and anything where you're digitizing continuous waveforms. And so it says for a signal in the time domain, which is band limited, if the sampling is done at a period of capital T, then the signal is uniquely determined by the samples, which are taken at integer multiples of capital T, if omega s is bigger than 2 times omega m. Okay, so just remember omega m was the maximum frequency component of the signal xt. So if your sample at more than twice that frequency, so if your sampling rate is more than twice that, then you will be able to reverse the process and fully recover the original continuous time waveform. If it's not that fast, then you will not be able to fully recover the original waveform. There will be ambiguities and distortions. And so 2 times omega m is called the Nyquist rate, after Nyquist, who came up with this theory. And omega m is called the Nyquist frequency. So that's an important distinction. It's often confused about the Nyquist rate and the Nyquist frequency. One of them is the frequency, which is the highest frequency component of your signal, and the other one is the rate at which you need to sample at. And then how do you go about recovering them from the samples? Well, it's shown there in the picture below. You've got your, it shows the signal coming in being multiplied by PT, which is the sampling waveform, to give you the sampled waveform, which is xpt, which is just the delta functions. And then if you put that through a filter, you can recover your original signal, as long as you design that filter appropriately. And in particular, if HT is the ideal low-pass filter, then you'll be able to recover the signal exactly, as long as you have sampled fast enough, higher than the Nyquist rate. And this shows the reconstruction of the original signal from the samples. So here's an ideal low-pass filter, and we've drawn the picture of it in the frequency domain here, in the omega domain, and it's ideal low-pass because it has a flat response, so all the frequencies pass through the filter as long as they are less than the cutoff frequency, omega c, and all the frequencies bigger than that are blocked by the filter. And you will recall from Fourier transforms that the inverse Fourier transform of the square shape there is a sinc function. So this is a square shape in the frequency domain, so the filter has a sinc impulse response in the time domain for the ideal low-pass filter. Now we call it the ideal low-pass filter not only because it's ideal in the sense that it's flat and all the frequencies are passing equally, but also in the sense that it's actually ideal and you cannot have this filter in reality, because it's impossible to have an impulse response that is a sinc function really that starts at negative infinite time and as you can see builds up to that peak at time equals 0 and then dies down for infinite time in the future. So in practice everything is time limited, and so therefore we're never going to be able to have exactly the low pass filter in practice. But you can see the maths there, and I encourage you to work through the maths to understand how the reconstruction happens mathematically as well as graphically in the pictures. And here's a graphical way in the time domain of visualizing what's happening with sampling. So at the top you've got the original signal, which is a smooth continuous time signal. Once it gets sampled with the train of delta functions or the series of delta functions all separated by capital T, then you get that series of delta functions where the heights of the delta functions correspond to the values of the signal at that exact time. And then the reconstruction happens by taking those impulses that you've sampled and convolving them with the sinc function. Because in the frequency domain, you're multiplying, that's what the filter is doing in the frequency domain, you're multiplying by that low-pass filter, ideal low-pass filter. What that means is in the time domain, you are convolving with a sinc function. And again, when you convolve with a sinc function, the sinc appears at the locations of the deltas when you convolve with a delta. So the sinc function convolved with each of those deltas is going to give you each of those black sinc functions with an appropriate height corresponding to the height of the delta, which is the sampled height. And then when you add up all of those sinc functions in the time domain, you will reconstruct the original signal, as long as you've sampled fast enough. And so that's a visual, graphical way of understanding the sampling and the reconstruction with an ideal low-pass filter. And then below that, it shows another filter, which is not ideal, but it's practically able to be realized, and that's the zero-order hold. That's what ZOH stands for. And so this has an impulse response which is a square, as shown in the black there, where it essentially holds the value for a period of time, capital T, and then returns to 0. And so when you convolve your stream of impulses, so the sampled function, the second one from the top, if you convolve that with the black square that's shown in the zero-order hold impulse response, then it will put a square at each of the places where there's a delta function with an appropriate height given by the delta function. And that's shown in the picture below with the blue heights with flat tops in the time domain. And you can see that it's an approximation to the green original signal. So this is one way of doing a practical reconstruction, because we can't do the ideal one with the ideal low-pass filter. We can't do the sinc functions in practice exactly. So one thing is to do a simple zero-order hold. And you can see that the reconstructed signal will be similar to the original signal, but in this blocked way. And that shows at the bottom the Fourier transform of the zero-order hold filter. And this shows a more advanced version of practical reconstruction compared to the zero-order hold. This is the first-order hold, and this is a linear interpolation between the sample points. So instead of going to the height of the delta function and holding it there as a constant, which was what happened for zero-order hold, now this is a way of interpolating between the delta function heights. And the way you do that is, as shown in the blue diagram there, the filter has an impulse response which is the triangle. So the impulse response of a triangle, which starts at minus capital T, rises up to a maximum at 0 and then dies down to 0 again at capital T. So again, if you convolve that with the XPT, the sampled waveform at the top, all those delta functions, you convolve that, you will get the picture that's shown below the blue block diagram. because the convolution will put that triangle centered at each of the delta functions from your sampled waveform, and then when you add them together, you will see that you get the black waveform below, which is a linear interpolation between the heights of each of the samples. And so this is again giving you a reconstruction. It's not exactly the original signal, but it is a practical reconstruction which can be done because the filter has a finite impulse response. It doesn't last forever like the sinc function did from the ideal low-pass filter. So this is another practical reconstruction method that is more accurate than the zero order hold. So this shows the effect of undersampling, which we call aliasing. So as mentioned previously, if you don't sample fast enough, then you'll get an overlap in the frequency domain. We call this aliasing. So this is when omega s is less than 2 times omega m. So don't forget, omega s is the sampling rate, the sampling frequency, and omega m is the maximum frequency of the signal, your original signal. So if you're sampling at a rate that's too slow, it's not bigger than twice omega m, then you're going to get overlap in the frequency domain, as we saw before and is drawn there. And if you then apply a low-pass filter, which is shown in green, the ideal low-pass filter, it's going to cut out all the frequencies above omega s. And so as shown in that black picture there, you're going to be getting the original part of the original signal between the omega s's, but you're also going to get the higher frequency components of the next copy mapped back in, we sometimes say folded back in, mapped back in to the frequencies within the minus omega s to omega s. And so this is going to disrupt your signal. So the high frequency components are getting mapped in, and in fact, I think you can see that the slower you sample, the more of the high frequency components get wrapped back in, as shown in that picture indicated in the black picture there. So this is the challenge when you have aliasing, in that you can't recover the original signal. And it also shows how the high frequencies become back as low frequencies. Also at the bottom it's mentioned there, noise in a system has a broad spectrum. It's across all the frequency bands. So a typical signal really looks like that picture that's shown there, where there's a small amount of all frequencies because there's noise in your sampling process. So you need to low-pass filter before you sample so that the high frequency noise doesn't get folded back into the reconstruction. And this is a figure that shows the effect of aliasing. So at the top two diagrams show that you've sampled, this is a slow changing sinusoid, and it's been sampled at those delta functions. And because it's low frequency, the sinusoid, for that sampling rate, when you reconstruct, you get the original signal back. And that's what's shown in the dotted. But if you had the same sampling rate, but you had a higher frequency sinusoid, which is the third picture down, then when you've sampled that waveform, when you reconstruct it, you would get the lower frequency waveform back. And this was because that frequency was too high for the sampling rate. Or another way of saying that is that the sampling rate was too low for that frequency. And what happened then, because the sampling rate was too low for that frequency, the high frequencies get wrapped back in and they appear as low frequencies in the reconstruction. And then the fifth and sixth diagram show an even more extreme case of that, where the signal is even higher frequency, which means relatively the sampling rate is even lower compared to that high frequency. And so when it reconstructs an even lower frequency. And you can confirm that for yourselves. If those sampling, it's drawn to scale and it's drawn accurately. You can see those sampling points in figures 1 and 2. The delta functions in figure 1 and 2 are identical. The delta functions in figure 2 and 3 are identical. And the delta functions in figure the delta functions in figure 3 and 4 are identical, and the delta functions in figure 5 and 6 are identical. And you can see that both of those waveforms, if you take 5 and 6 as an extreme example, both of the waveforms pass through exactly through those delta functions. So two different waveforms, but they pass through exactly the same set of delta functions. And so this is a visual example of the high frequencies wrapping back in and being reconstructed as low frequencies if you haven't sampled fast enough.